Welcome to the Deep Dive. Today, we are undertaking an expedition right into the heart of astrophysics.
Yeah, should be fascinating.
We've got this stack of complex sources, really detailed stuff on the life cycle of stars. We're not just talking about theory, but actual observational data.
Real proof.
Exactly. Proving how, where stars are born, how they keep shining for billions of years, and how they finally meet their end.
Right.
So our mission today is kind of to bring the life of a star off that theoretical graph, make it feel like a vibrant, ongoing process, maybe even touch on some of the quantum weirdness involved.
And that's crucial because it really defines the whole energy budget of the universe, doesn't it?
It really does.
And, if there's one big takeaway from all this material, it's how it just completely shatters that older kind of static view of the cosmos.
Well, the idea that everything just sort of popped into existence at once billions of years ago?
Exactly that. There was this, almost metaphysical idea that star formation was like a one-off event. Maybe all the stars formed roughly together way back when.
A finished universe just winding down.
Precisely. But modern astronomy, thanks to these incredible leaps in theory and our ability to observe things, it's proven star formation is ongoing. It's happening right now.
In our own galaxy.
In our galaxy and others, we've actually cataloged stars so young, they basically lit up when humans were already farming here on Earth.
That's a massive shift in thinking.
Yeah.
It means the galaxy is, still an active factory.
Very much in production, yeah.
And the evidence for this, it's not just philosophical, right? It's rooted in hard data, mapping young stars, looking at the gas around them.
Oh, absolutely. It's all about observation and stellar theory working together. So, yeah, to really understand the sun's future or any stars, we've got to start at the beginning, the birth process, which is, pretty spectacular.
Okay, let's unpack that journey. Where do we start? The ingredients.
Yeah.
How does a cloud of gas even decide to become a star?
Well, it kicks off with something called condensation theory. Sounds simple, but it's profound. Stars form when these huge clouds of gas and dust just floating in the interstellar medium, they collapse under their own gravity.
These giant molecular clouds.
Exactly. They start out cold, massive. But if a region inside gets dense enough, maybe a nudge from a nearby supernova explosion, something like that, gravity just takes over.
And we can actually see that this isn't happening randomly everywhere. Young stars pop up in specific galactic neighborhoods, right?
That's one of the key pieces of evidence. If you map out stellar associations, these are just groups of stars we know are young. They're not scattered evenly, not at all.
Where are they then?
Overwhelmingly, they're found in spiral arms of our galaxy.
Okay, so the nurseries are in the spiral arms. That points straight to the raw materials being there too.
It does. And then you bring in radio astronomy. That's the tool you need to map cold gas, the actual star building stuff. And guess what?
It's in the spiral arms too.
Yep. Heavily concentrated right there. The spiral arms are, without a doubt, the galactic nurseries.
And when we look at other nearby spiral galaxies, we see even more detail, don't we?
Oh, the detail is amazing. These detailed radio images show the absolute highest density of interstellar gas. The biggest pileup of building blocks is right on the inner edges of those spiral arms.
Inner edges. Why there specifically?
It's likely where the gas gets squeezed the hardest as the spiral density wave moves through. Compression is key.
Okay, so maximum compression on the inner edge. That's where we'd expect to see the immediate results of starbirth.
And that's exactly what we find when we switch to optical telescopes. Looking at those same inner edges, astronomers see HII regions, these big glowing clouds of ionized hydrogen gas.
Right, HII regions. They're kind of the smoking gun for recent massive starbirth, aren't they?
Absolutely the smoking gun. Think about what it takes to make that gas glow like that. Ionization needs a huge amount of energy, specifically powerful ultraviolet radiation.
Which only comes from certain types of stars.
Exactly. Stars that are incredibly hot, incredibly massive, and crucially, incredibly young. If you see an HII region, you know a big star switched on recently enough to still be blasting its surroundings with UV light. It just nails down that star formation is happening in the arms, and it's happening now, or at least very recently.
Okay, so gravity starts to collapse, the gas swirls in, we get this thing called a protostar. Why isn't it quite a star yet?
Well, the initial collapse happens fast. You get this dense, opaque ball of gas. But to be a proper star, like a main sequence star, the core needs to hit about 10 million Kelvin. Hot enough for fusion.
And this protostar isn't there yet.
Not even close initially.
So if it's not fusing, what stops it just staying cold and dark? Or just collapsing forever.
Its energy source is the collapse at first. The gas pressure inside isn't strong enough to fight gravity, so the sphere just keeps shrinking. And that contraction releases energy. Gravitational potential energy gets converted into heat, which radiates away.
That's the initial glow we'd see if we could see through the dust.
Right. And this whole gravitational contraction idea, it actually caused a lot of confusion historically.
Yeah, the Kelvin-Helmholtz timescale thing, right? They thought contraction powered the sun itself.
They did, back in the 19th century. Helmholtz and Kelvin. It was a brilliant idea for its time. They calculated that if the sun just shrank a tiny bit each year, it could generate the energy we see.
But the timing was way off.
Totally off. The big problem, as the sources point out, was the age of the Earth. Once radioactive dating showed Earth was billions of years old, the sun had to be too. Gravitational contraction could only power the sun for maybe, 10 to 30 million years, max.
So that theory died.
It did, for the sun's main energy source.
Yeah.
But the mechanism wasn't wrong, just misplaced. It's exactly what powers the protostar before fusion kicks in. So it's crucial, just only in that very early phase. Hashtag tag 1.2, observing the inevitable newborns.
Okay, so this protostar phase. It's dense, dusty, hard to see directly with visible light, and that led to some early mistakes.
It definitely did. Early on, astronomers using optical telescopes looked at these dark, dense patches called globules. They thought, aha, those must be the protostars.
Seemed logical, dark, dense. Looks like something collapsing.
Yeah, but it was a bit of the source calls it a naive view. Radio astronomy came along later and showed we weren't really seeing the earliest, densest collapse phase visually at all. It's hidden.
But we do see things like T-Tauri stars. They're related, aren't they? Kind of like stellar teenagers.
Exactly. T-Tauri stars are definitely confirmed pre-main sequence stars. They're past the initial protostar collapse, characterized by strong winds, lots of variability, often still wrapped in some gas and dust, but much more visible.
But seeing the actual very first moments, the birth cry, so to speak, that needed a different tool.
It needed radio astronomy, and the big breakthrough came quite unexpectedly back in 1966.
All right, this is the Mysterium story. Love this one.
It's a classic. Radio astronomers were just doing surveys, scanning the sky, and they stumbled upon these incredibly bright, super compact radio sources. They were emitting very strongly at an 18-centimeter wavelength.
The wavelength for the hydroxyl molecule,
Right,
OH, water-related.
Exactly. But the signal was so intense, so pinpointed, coming from such tiny spots. The scientists were just baffled. They thought, this can't be just plain old hydroxyl.
They literally thought it was a new element.
Initially, yeah.
Yeah.
They gave it the placeholder name Mysterium. It's funny because it echoes those earlier times in optical astronomy, with nebulum and nebulae and coronium in the sun's corona, unidentified bright lines. Which
turned out to be just familiar elements like oxygen, nitrogen, iron, but in really extreme conditions the labs couldn't replicate back then.
Precisely. And Mysterium's mystery was solved even faster. Within just a few weeks, they proved it was hydroxyl, just ordinary OH, but it was in an absolutely extraordinary physical state.
So the mystery wasn't the substance, but how it was shining so brightly.
Exactly. It wasn't the what, it was the how. This discovery basically opened up a whole new way to study the dynamics of star birth, right at the moment of creation.
And to even see these tiny sources clearly, they needed a revolutionary technique, right? VLBI.
Super long baseline radio interferometry. Yeah, VLBI was absolutely essential. You're basically linking radio telescopes thousands of kilometers apart, making them act like one gigantic telescope dish.
To get that incredible resolution.
Phenomenal resolution. We're talking a few thousandths of an arc second. To put that in perspective for you listening, that's like being able to see a human hair on the surface of the moon from here on Earth. About $3 times 10 radians. Just mind-bogglingly sharp vision.
And you need that sharpness to pick apart what's happening inside these stellar nurseries.
Yeah.
You mentioned the source W3.
W3 was a perfect example. The signal at 18 centimeters wasn't just one smooth peak. It was complex, made up of many separate, really narrow, bright spikes of emission.
Each spike a different little cloud.
Exactly. Each one corresponded to a tiny individual cloudlet, and crucially, they were moving at different speeds relative to us. We could measure that using the Doppler effect.
So it's not one collapsing blob, but a swarm of them.
A swarm, yeah. The observation showed maybe 10 or so of these compact clouds, all whizzing past each other, speeds differing by up to 10 kilometers per second.
Wow. And how big an area are we talking about?
The whole group was packed into maybe 1.5 arc second across. Translate that to distance, it's tiny, maybe 1/100th of a parsec. But the individual clouds themselves, Each one is only about the size of our solar system, maybe a bit bigger, like Earth-Sun distance times 10, roughly. Incredibly dense, turbulent little cocoons.
Okay, so why are these little, dense clouds shining so incredibly brightly in radio waves? This is the cosmic maser thing, right? Quantum physics in space.
Precisely. They realize these things are gigantic, natural cosmic masers. Maser stands for microwave amplification by stimulated emission of radiation, like a laser, but for microwaves.
How does that work in a gas cloud?
Well, a maser gets its huge brightness and that super narrow frequency because the gas, the medium, is activated. You need some kind of energy source, a pump, that forces way more molecules than normal into a higher energy state, an inverted population.
So they're all primed to emit energy.
Exactly. Then, when one molecule drops down and emits a photon, that photon stimulates others to emit identical photons in sync. You get this cascade, this coherent burst of amplified microwave radiation.
It's just amazing. We figure out how to build masers and lasers in the lab, and then find the universe has been doing it on a colossal scale all along.
Nature had it figured out billions of years ago. The conditions have to be just right, though. From the signal, we deduce these clouds are really dense, like 188 to 199 particles per cubic centimeter, mostly molecules.
Much denser than typical space clouds.
Way denser and relatively cool, probably around 1,000 Kelvin, definitely not hotter than 2,000 K.
That combination, dense and cool.
Yeah.
What does it resemble?
It strongly resembles the extended, cool outer atmospheres of supergiant stars. That comparison must have been a huge light bulb moment for the astronomers.
The vital clue.
It was. Linking the physical conditions to the emission mechanism led to the big realization. These maser sources are the earliest observable stage of protostars right after the initial condensation starts. They represent that violent initial adjustment phase when gravity really takes hold. Some people call them the cries of birth.
And how do we find them if they're buried so deep in dust?
Well, they're almost always found embedded inside these small, really dense cocoons of hydrogen gas. That gas makes them totally invisible optically because of the dust. But
Something lights up the cocoon.
often, yes. The ionization, the energy to make that cocoon glow slightly in radio waves, is usually provided by a nearby hot, massive star that formed just a little bit earlier in the same cloud complex. It's like the firstborn biggest star illuminates the nursery for its smaller siblings still forming.
Fascinating. And it wasn't just hydroxyl masers, right?
Yeah.
Other molecules got in on the act.
Yeah, about 2 years later, they found the same sources were also pumping out even stronger maser emission from water vapor, H2O, at a shorter wavelength, 1.35 centimeters. It just confirmed these star-forming regions are incredibly complex places, chemically and physically, driven by this intense gravitational collapse.
Okay, so gravitational contraction gets the protostar hot, it lights the masers. But that can't power a star for billions of years. Once the core hits that magic 10 million Kelvin, the real show begins.
Yeah.
The main sequence. But figuring out that power source was a huge scientific puzzle for a long time. Hashtag tag 2.1, the source of stellar energy.
Oh, it was the energy crisis of 19th and early 20th century physics, absolutely. The sun's output is staggering, right? $4 times 10 ergs every single second. The question was, how do you keep that furnace burning for billions of years?
We've already talked about how the contraction idea, Kelvin Helmholtz, failed the age test. Once we knew the Earth, and therefore the sun, was billions of years old, contraction just couldn't cut it.
Not even close. It was a fundamental roadblock. Scientists threw ideas around, meteorites constantly falling in, maybe some kind of chemical burning, but nothing provided that kind of longevity. The answer only came with the breakthroughs in nuclear physics in the late 1930s.
Nuclear fusion.
Thermonuclear fusion reactions happening deep in the core. That's the ticket.
When a core hits 177 Kelvin.
Exactly. At that temperature, protons' hydrogen nuclei are moving so incredibly fast they can overcome their mutual electrical repulsion, the force that normally keeps them apart. They slam together.
See.
And through a series of steps, primarily the proton chain in stars like the sun, 4 protons get converted into 1 helium nucleus. And crucially, a little bit of mass is lost in that conversion.
EMC squared.
That's the one. That tiny bit of lost mass transforms into a huge amount of energy, a sustained, powerful torrent.
And that energy doesn't just, explode out instantly.
No, it's a slow journey out. The energy, mostly in the form of photons, has to battle its way through the incredibly dense layers of the star. It gets absorbed, re-emitted, absorbed again. It sort of percolates outwards over maybe hundreds of thousands of years before it finally escapes from the surface as light and heat.
The efficiency must be incredible.
It's mind-blowing. If you calculate the sun's total energy budget, let's say it started as pure hydrogen, converting all of that to helium would release something like 1050 ergs. But here's the kicker. To maintain its current brightness for billions of years, the sun only needs to fuse less than 10% of its original hydrogen fuel.
Wow. So it has tons of fuel left.
Plenty. That efficiency is what provides the stability for billions of years.
So fusion starts, energy flows out, and the star finds its balance.
That's the definition of landing on the main sequence. The tremendous outward pressure created by the fusion heat finally balances the inward crush of gravity. The star stops contracting, it settles down, and it finds its specific place on that famous Hertzsprung-Russell diagram, the HR diagram.
The place where it can just sit and steadily burn hydrogen for a long, long time.
Exactly. It's stable. Adult life begins. Hashtag 2.2, the crucial role of mass and composition.
Okay, so a star lands on the main sequence. What determines where it lands on that diagram? Is it just about how big it is?
Mass is definitely the #1 factor, the primary determinant. Think about it. A more massive star has way more gravity trying to crush it.
So it needs more outward pressure to balance things.
Right, which means its core has to be hotter and denser to drive fusion reactions much, much faster. So more massive stars are hotter, they're way more luminous, brighter, and that puts them up towards the top left of the HR diagram, blue and bright.
But the sources mentioned there's a second factor too, something more subtle that causes variations, like that subdwarf sequence.
Yes, the second parameter. That's the star's initial chemical composition. Specifically, what astronomers often lump together and call metallicity. Basically, the abundance of elements heavier than hydrogen and helium.
Stuff like carbon, oxygen, iron.
All that. Stars that formed really early in the universe, before many heavy elements had been created by previous generations of stars, have lower metallicity.
Yeah.
And that affects how they behave.
How so?
For a star of a given mass, if it has less heavy element content, it tends to lie lower on the HR diagram compared to a star of the same mass, but with more metals.
And that explains the subdwarfs. They look dimmer or maybe smaller for their mass.
Exactly. They have heavy element abundances, maybe tens of times lower than stars like our sun. It changes their internal structure and how energy gets out.
Okay, so mass is king.
Mm-hmm.
Composition is like a secondary influence on position.
Yeah.
But mass does something even more fundamental, right? It dictates the star's entire lifespan.
Oh, absolutely. Mass is the cosmic clock controlling how long a star lives, especially its time on the main sequence.
And the range is huge.
It's dramatic. You look at the real heavyweights, those hot blue O-type stars, maybe dozens of times the sun's mass. Their cores are like raging infernos to support their weight. They burn through their hydrogen fuel ridiculously fast. We're talking just a few million years. Their brilliance is incredibly intense, but incredibly short-lived. They live fast, die young.
Whereas our sun gets a much more leisurely pace.
Much more. Sun-like stars, G-type stars, they hang out on the main sequence for a good 10 to 15 billion years.
Okay, and what about the little guys? The dim red dwarfs.
The cosmic marathon runners. Those stars, the ones less massive than maybe a K-Euro-type star, they sip their fuel so incredibly slowly. Their calculated main sequence lifetimes are just staggering.
Longer than the age of the universe.
Significantly longer.
Yeah.
Much longer than the current estimated age of the galaxy, which is maybe 15 to 20 billion years.
So wait, does that mean that the very first low-mass stars that formed when the galaxy was young, they're still around, still on the main sequence?
That's exactly what it means. If a red dwarf formed 13 billion years ago, it's still sitting there, happily fusing hydrogen, maybe only partway through its fuel supply. They haven't had time to evolve off the main sequence yet.
Wow. They're essentially immortal on timescales relevant to us.
Pretty much. It really underscores just how incredibly long these stellar lifetimes can be, especially at the low mass end.
Okay, but even the longest life has an end. For stars massive enough to have evolved by now, what happens when that core hydrogen finally runs out? That's when things get interesting, right? They leave the main sequence. Hashtag 3.1, leaving the main sequence.
Yeah, things definitely get more dramatic. The crucial point to remember is that the hydrogen fusion, the burning, only happens down in the super hot, super dense core.
And the rest of the star's hydrogen just sits there.
Pretty much. There's generally no large-scale mixing between the core and the outer layers, the envelope. So the envelope keeps its pristine hydrogen, while the core converts all its hydrogen into helium.
Okay, so the core runs out of fuel, fusion stops. What happens then?
Gravity wins again, instantly.
Hmm.
With the outward pressure from fusion gone, the core, now mostly helium, starts to contract under its own weight. And as it contracts, it heats up a lot.
It gets denser and hotter.
Very dense, very hot. It forms this compact core of helium ash. And the gas in that core enters that weird quantum state we mentioned earlier. Degenerate gas.
Right, where the pressure comes from electrons being squeezed too close together, not from temperature.
Exactly. Degeneracy pressure. It provides support, but the core is still incredibly hot.
So the core shrinks and gets super hot, but the star itself, it does the opposite, right? It balloons into a red giant. That seems counterintuitive.
It does seem weird. But here's how it works. That contracting, incredibly hot helium core acts like a furnace heating up the layers just outside it, and the layers still contain unburnt hydrogen.
Ah, so fusion restarts, but not in the core.
Exactly. The heat from the collapsing core becomes intense enough to ignite hydrogen fusion in a thin shell surrounding the dead helium core. And because this shell is now under immense pressure from the layers above and being heated intensely from below,
It burns really, really fast.
furiously fast. This hydrogen-burning shell produces far more energy, far more luminosity than the star ever did when it was quietly fusing hydrogen in its core on the main sequence.
And all that extra energy pouring outwards.
Pushes the star's outer envelope, the vast majority of its volume, outwards, way outwards. The star swells up enormously, becoming hundreds of times larger in radius. Its surface cools down because the energy is spread over such a huge area, so it looks reddish.
Hence, the red giant phase. It moves up and to the right on the HR diagram.
Precisely. And again, that metallicity factor plays a role here too. Remember the low metal stars?
Yeah.
Well, if you have two red giants of the same physical size, the one with lower metallicity will actually be significantly more luminous. The lower metal content affects how easily energy escapes the star, its opacity. Hashtag 3.2 observational proof from star clusters.
This whole theoretical track main sequence to red giant sounds plausible, but how do we know it's right? This is where star clusters come in again, isn't it? They're like time capsules.
They are perfect cosmic laboratories. The key thing about a star cluster, whether it's an open cluster or a globular cluster, is that all the stars inside formed at pretty much the same time, from the same initial cloud of gas and dust.
So they have the same age and the same starting composition.
Exactly. That means any differences we see among them now are purely down to one thing, their initial mass, which dictates how fast they evolve. So, plotting an HR diagram for a cluster gives us a snapshot of stellar evolution at a specific age.
Okay, let's compare. Take a young open cluster, like NGC 2254 mentioned in the sources. What does its HR diagram look like?
It looks, well, young. You see the whole main sequence nicely populated all the way up to the hot, bright, massive blue stars in the upper left. Those guys are still there because the cluster hasn't been around long enough for them to burn out yet.
And the red giant part.
The red giant branch is pretty sparse. Only the absolute most massive stars, the ones that live just a few million years, have had enough time to exhaust their core hydrogen and swell up. Most stars are still on the main sequence.
Okay, now contrast that with a really old system, like a globular cluster. M3 is the example given.
M3 is ancient, maybe 10, 12 billion years old. Its HR diagram tells a completely different story. The top part of the main sequence, it's gone, empty.
Scraped clean.
Utterly scraped clean. All those massive, bright blue stars that were maybe there originally, they burned out billions of years ago. Instead, what dominates the diagram now?
The red giant branch.
A huge, prominent red giant branch. This shows that over those billions of years, thousands of stars with masses more like the sun's have had time to finish their main sequence lives, exhaust their cores, and evolve off into the giant phase.
So the point on the main sequence where stars seem to turn off and head towards the giant branch, that point tells you the age of the cluster.
Precisely. It's called the main sequence turn-off point, and it's one of the most reliable ways we have to determine the ages of star clusters and, by extension, constrain the age of the universe itself.
And what about the shape of that giant branch? Does metallicity show up there too?
It really does. Remember we said lower metallicity giants are more luminous? Well, the giant branch for old, metal-poor M3 goes very steeply upwards on the HR diagram, high luminosity. But for young, relatively metal-rich NGC 2254, the short giant branch it has is almost horizontal.
Lower luminosity for its temperature.
Exactly. That difference in the branch shape is explained perfectly by M3 having much lower heavy element content, which is typical for those ancient stars concentrated towards the galaxy's center. Observation beautifully confirms the theory, including the role of composition, #tagged #3.3, the next nuclear phase.
Looking closely at that HR diagram for the old cluster M3, there's another feature, isn't there? Besides the main sequence and the red giant branch, there's like a separate clump of stars, almost horizontal.
Yes, the horizontal branch. That's absent in young clusters like NGC 2254, but very prominent in old ones like M3. It represents the next stage of evolution after the star becomes a red giant.
What triggers this? Is it the helium core doing something?
It is. While the star is a red giant burning hydrogen in that shell, the helium core itself keeps contracting under gravity, getting hotter and denser. Remember, it's degenerate.
Right.
Eventually, the temperature in that contracting helium core reaches a truly staggering level, somewhere between 100 and 150 million Kelvin.
Whoa. Okay, that must be hot enough for helium itself to start fusing.
That's exactly what happens. A new nuclear reaction kicks in, the triple alpha process. 3 helium nuclei, which are also called alpha particles, fuse together to form one nucleus of carbon-12.
Helium into carbon, the next step up the elemental ladder.
Right. In stars like the Sun, this helium ignition can happen very suddenly, almost explosively within the core, an event called the helium flash. Though, interestingly, the outer star doesn't show much immediate outward change because the energy gets absorbed internally.
But the key thing is, the core now has a new energy source.
Yes. Helium fusion starts providing energy, generating pressure. This finally halts the contraction of the core. The core stabilizes again, now burning helium instead of contracting.
And how does that affect the outside of the star? Why the horizontal branch?
With the core stabilized and burning helium, the overall structure adjusts. The hydrogen-burning shell might change its rate, the energy balance shifts, and crucially, the star's outer layers actually heat up a bit, and the star might shrink somewhat from its peak red giant size. This causes it to move leftwards on the HR diagram towards hotter surface temperatures, but maybe similar luminosity, settling onto that horizontal branch we see in M3. #3.4. The fate of low-mass stars, the sun's end.
Okay, so hydrogen burns to helium in the core, then hydrogen burns in a shell while the helium core contracts, then helium ignites and burns to carbon in the core. What happens when the helium runs out in the core? For stars like our sun, say, less than about 1.2 times its mass, is that the end of the line for fusion?
For stars in that mass range, yes, that's pretty much the end of fusion. The core, now mostly carbon and maybe some oxygen, will start to contract again. It gets incredibly hot, but for these lower mass stars, it never quite reaches the maybe 600 million Kelvin needed to ignite carbon fusion.
So the core just stops, supported by that degeneracy pressure again.
Exactly. The core becomes a super dense ball of carbon and oxygen, supported entirely by electron degeneracy pressure, no longer generating energy via fusion. But the star itself undergoes one last dramatic transformation. It basically sheds a huge fraction of its outer layers.
Throws off its envelope.
Yeah, a significant portion of its mass is ejected out into space. This process, the shedding of the outer layers, is what we observe as a planetary nebula.
Which aren't actually related to planets, despite the name.
Not at all, just a historical name because through early small telescopes, they looked like faint greenish disks, maybe resembling Uranus or Neptune. But what's really happening is the star's outer envelope is expanding away relatively slowly, like a smoke ring.
And what's left behind in the center?
What's left is the incredibly hot, incredibly dense core remnant, the carbon-oxygen core we just talked about. It's now exposed, and it's still blisteringly hot, maybe hundreds of thousands of degrees on its surface initially.
And that hot core lights up the gas cloud around it.
Precisely. The intense ultraviolet radiation pouring off that tiny hot central star, which we now call the planetary nebula nucleus, ionizes the expanding gas shell that the star just threw off.
Making it glow beautifully, those amazing shapes we see in Hubble images.
Those exact ones. But it's a fleeting beauty. That glowing phase only lasts for maybe tens of thousands of years, relatively quick in cosmic terms.
And after the gas cloud disperses and fades away, what remains?
What's left is just the central star itself, the small, super dense cooling core. That is a white dwarf. and that's the final evolutionary stage for something like 97% of all stars in the galaxy, including our sun eventually.
A stellar remnant,
Okay.
effectively dead, right? No more fusion.
Completely dead in terms of energy generation. A white dwarf is a stellar corpse. It contains basically no hydrogen. Nuclear reactions have ceased entirely. It's supported against gravity only by that quantum mechanical electron degeneracy pressure.
And they're tiny but massive.
Incredibly dense. They typically have a mass comparable to the sun, maybe 0.6 to 1 solar mass, but squeezed into a volume about the size of the Earth. That means their density is millions of times greater than water. A teaspoonful would weigh tons.
Just staggering. And what's the very, very final stage? Does it just sit there forever?
It just cools down. Since it has no internal energy source left, it radiates away its stored heat into space. Very, very slowly, over hundreds of millions, even billions and billions of years.
Until it fades from view entirely.
Eventually, yes. Theoretically, it cools down so much it no longer emits significant light, becoming a cold, dark, stellar cinder, what astronomers call a black dwarf. Though the universe isn't old enough yet for any white dwarf to have cooled down that completely. Hashtag 3.5, the sun's timeline.
So if we apply this whole evolutionary story to our own sun, we can actually map out its future.
We can, with pretty good confidence based on stellar models. The sun formed about 5 billion years ago, quite a while after the galaxy itself got started. And it's been chugging along happily on the main sequence for about 4.5 or 4.6 billion years now.
So it's middle-aged.
Definitely middle-aged. Solidly in its prime hydrogen-burning phase.
How much longer does it have in this stable phase?
The calculations suggest the sun's got about another, maybe 5 billion years or so left on the main sequence. Something like that. Then the changes begin.
When does it become a red giant?
It'll start that transition probably around 5 to 6 billion years from now. So roughly when it's about 10 or 11 billion years old in total.
And the effects on Earth and the solar system will be dramatic.
Oh, utterly catastrophic for the inner planets. During its red giant phase, the sun's luminosity will swell maybe hundreds, even thousands of times its current brightness. And its physical size, its radius, will increase enormously.
Engulfing planets?
Definitely Mercury and Venus. Earth's fate is a bit more borderline in the models. It might be swallowed, or it might end up orbiting just outside the bloated sun, but completely roasted, obviously. Either way, Earth becomes uninhabitable long before that.
How long does that red giant phase last?
The peak giant phase might last for a few 100 million years, maybe a bit longer. Then it'll go through that final stage we discussed.
Shed its outer layers as a planetary nebula.
Exactly. Create a beautiful planetary nebula for future alien astronomers to admire, maybe, and leave behind a white dwarf remnant.
Which will then just slowly cool off for trillions of years. A quiet end.
A very quiet, very slow fade into darkness. That's the sun's ultimate destiny.
It's already amazing that we can model these stages happening billions of years from now or light years away. But the theory of stellar interiors, how stars work on the inside, it suggested we could do something even wilder, directly measure the conditions inside our own sun's core now.
Right, and that direct check comes courtesy of a tiny, almost undetectable particle, the neutrino.
The ghost particle.
The ghost particle, indeed. Neutrinos are produced as a fundamental byproduct of the nuclear fusion reactions, the proton chain that power the sun. So if our model of the sun's core is right, it must be pumping out an absolutely enormous number of neutrinos constantly.
And neutrinos are perfect messengers in theory because they barely interact with anything, right?
That's their key property, and what makes them both valuable and incredibly difficult to detect. They interact via the weak nuclear force, which is, well, weak. A typical neutrino produced in the sun's core can fly straight through the entire sun, billions of miles of super-dense plasma, without hitting anything.
Like almost zero chance of interaction.
Almost zero. Maybe only one in, say, tens of millions or even billions of solar neutrinos actually interacts with any matter on its way out.
But that means the ones that do get out carry information directly from the core unchanged.
Exactly. Unlike photons, which bounce around for millennia, neutrinos zip straight out at nearly the speed of light, carrying direct, real-time information about the fusion reactions happening deep inside. The temperature, the density, the specific reactions occurring.
It's like having a probe right inside the sun's furnace.
It is. And the energy carried away by these neutrinos isn't trivial either. It's expected to be several % of the sun's total energy output.
Okay, so how do you even begin to detect these things if they barely interact? This led to that famous experiment concept, proposed by Pontecorvo.
Bruno Pontecorvo, yes. And later refined and implemented by Ray Davis Jr., who eventually won a Nobel Prize for it. The ingenious idea was to use a specific nuclear reaction that neutrinos can trigger, even if rarely. They focused on chlorine-37 text.
What happens when a neutrino hits chlorine?
If a solar neutrino, specifically an electron neutrino, the type produced in the main solar fusion, hits a chlorine-37 nucleus, it can transform the chlorine into a radioactive isotope of argon, argon-37, and an electron is also emitted.
So you look for the argon atoms.
That's the trick. Argon-37 is radioactive. It decays with a known half-life. So the idea was to get a huge amount of chlorine, shield it from other radiation deep underground, let the solar neutrinos interact with it, and then periodically, painstakingly flesh out and count the tiny number of argon-37 atoms created.
And a huge amount means really huge.
Gargantuan. Ray Davis's experiment used a massive tank filled with over 600 tons, that's hundreds of thousands of liters of perchloroethylene, which is basically dry cleaning fluid, very rich in chlorine. It was located deep underground in the Homestake gold mine in South Dakota to shield it.
Wow. And this setup acted like a thermometer for the sun's core.
In a way, yes, because the rate at which argon-37 atoms are produced depends very strongly on the energy of the incoming neutrinos. And the neutrino energy spectrum, in turn, is super sensitive to the precise temperature inside the sun's core, according to the standard solar model.
Okay, so they ran this incredibly difficult experiment for years. Decades, actually. What did they find? Did it confirm the models?
It was a shocker, a real bombshell in astrophysics. The experiment consistently detected only about 1/3 the number of solar neutrinos that the best theoretical models of the sun predicted should be there.
1/3. Not like a small error margin, but a huge discrepancy.
A huge, persistent discrepancy. It became known as the solar neutrino problem, and it caused immense turmoil. Did it mean our understanding of nuclear fusion was fundamentally wrong? Was the sun's core somehow much cooler than we thought? Were our models of stars just broken?
What was the answer? Did they have to rewrite stellar physics?
This is the beautiful part of the story. The sources note this, and it's crucial. The problem wasn't actually with the model of the sun. The solar model, the astrophysics, turned out to be remarkably accurate. The problem was with our understanding of the neutrino itself.
So it was particle physics, not astrophysics.
Exactly. We had assumed neutrinos were massless, or at least that they didn't change their type. The solution, confirmed by later experiments like the Sudbury Neutrino Observatory, SNO, in Canada, was the discovery of neutrino oscillation.
They can change flavor.
Yes. There are 3 flavors of neutrinos: electron, muon, and tau. The sun produces only electron neutrinos. But as they travel from the sun to the Earth, they can spontaneously change or oscillate into muon or tau neutrinos. Davis's chlorine experiment was primarily sensitive only to the electron neutrinos.
So the electron neutrinos were disappearing by changing into types his detector couldn't see.
Precisely. SNO was able to detect all 3 flavors and showed that if you added them all up, the total number of neutrinos arriving from the sun perfectly matched the predictions of the standard solar model. It was an incredible triumph.
Wow. So the crisis actually led to a fundamental discovery about particle physics and confirmed our model of the sun's interior was correct all along.
That's exactly right. It shows how interconnected these fields are and how testing astronomical theories can lead to breakthroughs in fundamental physics and vice versa. Hashtag 4.2 synthesis and final thoughts.
Looking back over this whole journey then, from collapsing clouds and masers to white dwarfs and neutrinos, the theory of stellar evolution really stands out as a monumental achievement of 20th century science, doesn't it?
Oh, absolutely. It required this incredible synergy. You needed the painstaking work of observers building those HR diagrams for countless stars and clusters. You needed nuclear physicists in labs to measure the precise rates of fusion reactions. And you needed the sheer power of computers to run the complex calculations modeling a star's interior over billions of yen.
Theory, observation, computation, lab physics, all coming together.
A perfect storm of scientific collaboration.
And the big picture that emerges is that this isn't just ancient history. Star formation is ongoing. The cosmic clock is still ticking. Creation hasn't stopped.
Right. That continuous process is why we still see those brilliant, massive O and B stars blazing away at the top of the main sequence. They're the youngsters, the new arrivals, constantly replenishing the population, although
the rate has slowed down.
Yeah, the sources do confirm that. The overall rate of star formation in galaxies like ours today is significantly lower than it was way back, billions of years ago in the early universe. The peak baby boom is over.
And thinking about those timescales, it helps us date the galaxy itself, right? Based on which stars have had time to evolve off the main sequence.
Exactly. If we estimate the galaxy is, say, 15 to 20 billion years old, then only stars more massive than a certain threshold have actually completed their full life cycle and died. That threshold mass is maybe only 10 or 12% more massive than our sun.
So any star less massive than about 1.2 solar masses,
Right.
even if it formed right at the beginning of the universe, is still on the main sequence today.
That's right. The vast, vast majority of stars that have ever formed, the lower mass ones, haven't even reached the red giant stage yet, let alone the white dwarf stage. They're still burning hydrogen.
It puts our sun's upcoming demise in perspective.
Hmm.
It's relatively early in the grand scheme of stellar death.
Very much so.
So we've tracked this incredible life, gravity kicking things off with quantum masers, then billions of years of stable fusion power, the dramatic expansion into a red giant, maybe a helium burning phase, and finally, for most, that slow fade as a white dwarf.
You know, what really stands out to me in all this is the synthesis of physics, especially energy physics. We saw incredibly advanced quantum radiophysics masers operating naturally inside collapsing clouds. And then you have the core of a star, solving the very energy problem sustained thermonuclear fusion that humanity is still struggling to perfect and control down here.
The universe as the ultimate fusion engineer.
Absolutely. It cracked it billions of years ago.
So we know the end state for most stars.
Yeah.
That cold, dense black dwarf eventually. The sun's light will fade billions of years after Earth is gone. But considering that star formation is still happening, even if more slowly, and that most existing stars won't die for literally trillions of years, what does that incredibly long, drawn-out process of birth and death imply for how we think about the future of energy and light in the universe?
That's the really profound final thought, isn't it? It suggests the universe won't just switch off suddenly. It's facing this incredibly long, slow decline. A universe increasingly dominated not by bright stars, but by the cooling embers, white dwarfs, slowly fading over unimaginable timescales, eventually becoming those black dwarfs. Trillions upon trillions of these cold, dense, planet-sized remnants. What does that ultimate dominance of cold, dead stars, this slow winding down over perhaps hundreds of trillions of years, what does that imply for future galactic history, for entropy, for the very concept of time on a cosmic scale?
A universe slowly fading to black.
That's the lingering question the stars leave us with.